Imagine if numbers were not a human invention, but rather a profound discovery. What if the equations we use are not merely tools to describe the universe, but are instead clues pointing toward its true identity? If you look closely, the spiral of a galaxy, the orbital dance of the planets, and the rhythmic beating of a human heart all follow invisible laws written in a mathematical language. Before we begin this exploration, I invite you to share your own goals and aspirations in the comments. Perhaps they are closer to realization than you think. What follows is a dense and deep journey, so I encourage you to listen intently or let it guide you into a thoughtful sleep. These patterns are not coincidences, they are a deep signature of something far more fundamental. For centuries, we have used mathematics to calculate, to build, and to predict, but perhaps we have misunderstood its true purpose. What if math is not just a bridge to the universe, but is the universe itself? From the smallest particle to the largest cosmic structure, everything follows patterns that originate not from physical matter, but from pure, abstract logic. The universe begins to look less like a machine and more like a mathematical theorem. In this documentary journey, we will move beyond formulas and step into a realm where numbers breathe and geometry shapes reality, a place where the fabric of existence might simply be mathematics taking physical form. This is more than science, it is a search for meaning and truth, exploring the underlying structure of everything we know. This is the essence of the mathematical universe. The story is long, so let us begin this dreamlike descent, but before we start, remember to like and share. Long before we built computers, launched rockets, or wrote equations on a blackboard, mathematics already existed, etched into the very fabric of the natural world. It appears in the spiral of a shell, the rhythm of the tides, and the way a leaf unfurls toward the sun. No one wrote these laws, they exist independently of us, silently governing the operations of reality. We did not invent this, we discovered it. The earliest mathematicians were not scientists in lab coats, but farmers tracking the seasons, builders aligning monuments to the stars, and witnesses to the recurring patterns of nature. They noticed that certain events repeat with mechanical precision. Mathematics began with the most primitive counts: 1 seed, 2, 3, a full moon that vanishes and returns. From daily cycles to the movement of the tides, early humans saw that nature was rhythmic and repeatable. As civilization progressed, these patterns moved beyond simple cycles into breathtaking precision. Perhaps the most famous is the Fibonacci sequence, where each number is the sum of the two preceding it. This simple numerical game appears in the most unexpected places. Consider the sunflower, its seeds are not scattered randomly but arranged in spirals. If you count these spirals clockwise and counterclockwise, you will almost always find Fibonacci numbers, perhaps 34 in one direction and 55 in the other. Pine cones, pineapples, and even the branching of trees follow this same sequence, as if nature follows an invisible blueprint to determine growth in the most efficient way possible. This sequence is tied to the golden ratio, a number roughly equal to 1.618, which has fascinated artists and scientists alike. The golden spiral derived from this ratio appears in hurricanes, galaxies, and nautilus shells because it provides the most effective arrangement for balanced growth and harmony. It is not just beautiful, it is practical. Evolution seems to favor mathematics. The relationship between nature and math extends into the realm of geometry. Snowflakes are a hallmark of this idea. Each one is a crystalline wonder of six-sided symmetry, determined by the way water molecules bond at low temperatures. Despite the chaotic environment of their formation, their hexagonal logic remains precise. No two are identical, yet all follow the same geometric rules. Bees, too, are masters of geometry. Their honeycombs are made of perfect hexagons, a shape that allows them to store the maximum amount of honey using the minimum amount of wax. Mathematically, the hexagon is the most efficient shape for tiling a surface without leaving any gaps. Through instinct, bees arrived at a solution that would impress even the most seasoned engineer. Spider webs rely on radial symmetry, lightning spreads in fractal patterns, and the human lung branches into a recursive structure to maximize surface area for gas exchange. These are not just biological traits, they are geometric solutions to physical problems. Mathematics permeates time as well. The frequency of bird songs is predictable, and certain cicadas emerge only every 13 or 17 years, both prime numbers perhaps to avoid the life cycles of predators. Our heartbeats, our blinks, and the firing of our neurons all follow patterns of frequency and amplitude that can be modeled with mathematical precision. Even music, the most emotional of human expressions, is essentially mathematical. Notes are defined by frequencies, and harmony arises from simple integer ratios between those notes. Nature prefers these ratios, which is why some chords sound pleasant while others feel discordant. It is a matter of mathematical waves either aligning or clashing. These rhythms live within us, as circadian rhythms govern our sleep, our hormones, and our energy. Life, at every level, obeys the laws of mathematics and time. We must wonder if these ideal forms truly exist and if they dictate the shape of our world. When you close your eyes and imagine the number 3, where does it exist? It is not on the paper, it is not in the air, and it is not in the physical world, yet it exists nonetheless. Circles, squares, and triangles do not appear in perfect form in nature, yet we all understand what a perfect circle is. The laws of arithmetic do not need a universe to exist in order to be true. 2 plus 2 will always equal 4, even if all matter were to vanish tomorrow. This leads to one of the most provocative ideas in philosophy, that numbers, shapes, and mathematical truths exist in their own realm, independent of the physical universe. This is the domain of Platonic realism. The Greek philosopher Plato argued that the world we perceive with our senses is merely a shadow of a deeper reality. He believed everything we see, trees, mountains, people, stars, is an imperfect reflection of an ideal form. A circle drawn in the sand is imperfect, but the concept of a perfect circle exists beyond time and space. It is a truth that was never created and cannot be destroyed. In this framework, we do not create triangles or define the number 7, we reveal them. They were already there, waiting to be seen. This might sound abstract, but consider why mathematics works so well. Why can equations written by humans predict the behavior of stars and subatomic particles with such startling accuracy? Why does something created in the mind align perfectly with physical systems? If math were just a human tool, why would it be so reliable at predicting phenomena we haven't even observed yet? History shows that abstract mathematical structures are often imagined on paper first, only to be discovered later as the exact description of reality. Imaginary numbers seemed nonsensical at first, yet they are the key to understanding electrical circuits and quantum mechanics. Non-Euclidean geometry was once pure theory, but Einstein used it to describe the curvature of space-time. It seems mathematics knows things we do not, and we are merely catching up. To a Platonist, this is no mystery. Math is not invented, it is the skeleton of reality, existing in a timeless dimension where every truth resides. We do not write mathematics, we receive it, like a signal from a deeper realm. If this is true, then there is a universal library of every possible mathematical structure, floating in a dimensionless space, and our universe has somehow plugged into it. Perhaps reality is not shaped by matter, but by mathematics. We ourselves might be projections of pure patterns, so pure they are invisible. This idea is both mystical and deeply rational. When a mathematician discovers a new theorem, is a new thing born, or was it simply found? Even those who don't follow Plato often describe mathematical insight as a discovery, as if the truth were already there, waiting for the veil to be lifted. If these forms are eternal, they are older than the stars, the atoms, and time itself. They exist as relationships and structures that don't need a universe to be true. If so, the universe itself might be an imperfect manifestation of these hidden forms, unseen logic projected into visible matter. This leads to a deeper question: are we part of a mathematical structure, or are we just observers? If we are made of the same logic we study, then understanding math is like looking inward at the framework of our own existence. We are thinking matter contemplating its own source. But in a mathematical universe, what does life mean? Are we free, or are we bound by unbreakable equations? If math is the ultimate reality, does free will exist, or are we just trajectories in a multidimensional equation, unfolding with cold elegance? Even in this determinism, there is room for awe. The deeper we explore math, the more we find beauty and interconnectedness. Equations from different fields often converge. A formula used in genetics might explain the statistics of a black hole. These are not accidents, they are echoes of a deeper unity. If mathematical forms exist outside of time and space, then the universe is not just a machine made of particles, but an embodiment of thought, not our thought, but thought itself. It is a logic without a thinker, a language without a speaker. The universe becomes a poem written in invisible symbols, and every atom obeys it. Ultimately, Platonic realism is not just a philosophy of numbers, it is a view of existence suggesting that the material world is not the final reality. Behind the dust and the stars lies a structure of forms, not particles. To study math is to explore the foundation of the cosmos. Some go even further, suggesting the universe is not just described by math, but is math. This hypothesis, known as the mathematical universe hypothesis, proposed by physicist Max Tegmark, is as radical as it is bold. It suggests the universe is not a canvas painted with equations, but is the canvas, the paint, and the frame itself. In this view, every particle, every force, and every moment is a mathematical structure existing independently of human thought. We are not observers in a mathematical realm, we are conscious expressions of abstract relationships. Tegmark describes a reality where the ultimate foundation is not matter or energy, but logic. An electron is not a tiny ball, but a manifestation of mathematical symmetry. Space is not a void, but a topology defined by sets of relationships. Time is not a flowing river, but a complex multidimensional structure. If our universe is a mathematical structure, then every other consistent mathematical structure must also exist. This implies a multiverse of all possible mathematical systems, each as real as our own, with its own constants and dimensions. We happen to live in one that supports observers. Our reality is just one node in an infinite mathematical landscape. This hypothesis dissolves the mystery of why math is so effective in physics. It is effective because there is no difference between the two. We are discovering the face of the structure we inhabit. This view brings a new perspective to the chaos of nature, suggesting that beneath the surface, everything is built on formal logic. But it also raises questions about our experience of time and change. If all mathematical truths are eternal, where does our experience of the now come from? It is suggested that consciousness emerges in structures complex enough to model themselves and their environment, perceiving a sequence of states we call time. Our memories and anticipations are byproducts of being embedded in such a structure. Even our emotions and creativity might be seen as emergent properties of these mathematical relationships. This model unites science and the search for meaning, viewing the universe not as a place, but as a proposition, not a miracle, but a manifestation. Life is not an accident, it is a mathematical necessity in certain structures. We exist because the way the universe is structured made our emergence inevitable. We are not just observers of the cosmic machine, we are patterns within a self-aware equation, dreaming among the stars, held together by the elegant symmetry of the laws of nature. These groups possess enigmatic names like Su, 3, Su, 2, and U, 1. They are not arbitrary constructions but are the fundamental fingerprints of the laws of nature. Every known fundamental interaction, electromagnetism, the weak force, and the strong force, originates from the requirement that physical laws must remain invariant under specific transformations. Gauge symmetry is the cornerstone of these interactions. It ensures that within an abstract mathematical space, the behavior of particles remains consistent even as we shift our perspective. This is not the symmetry of space or time as we commonly understand it, rather, it is a symmetry of internal fields, a rotation in invisible dimensions, or an exchange of charge and phase. These define the very consistency of reality. When you alter a field in a way that respects these symmetries, the physics remains unchanged. This invariance gives rise to forces. In this view, a force is not a push or a pull, but a compensation made by nature to preserve its internal symmetry. The photon exists because of the invariance of the U1 gauge transformation. Gluons hold the atomic nucleus together because of SU3 symmetry. Even the Higgs field, which endows particles with mass, arises from the concept of symmetry breaking, where a perfectly symmetric system spontaneously chooses a direction, creating the illusion of asymmetry. Spontaneous symmetry breaking is itself a profound mystery of the universe, much like a pen balanced on its tip that eventually falls in a particular direction. In the early universe, when energy levels were unimaginably high, the forces of nature were unified and indistinguishable. But as the universe cooled, this symmetry shattered, and the unified force split into the four distinct interactions we observe today: gravity, electromagnetism, the strong force, and the weak force. The emergence of structure, complexity, and diversity is the direct product of this broken symmetry. Yet, this breaking is not chaos, it is a higher order disguised as diversity. The laws of nature were not born despite the breaking of symmetry, but because of it. Even the flow of time from the past to the future may be attributed to a deep symmetry broken at the dawn of the cosmos. Symmetry also defines the boundaries of possibility. It explains why certain particles decay while others remain stable, why matter exists while antimatter is scarce, and why particles moving through the vacuum interact with some fields and not others. All of this stems from the geometric rules of symmetry embedded in the equations of the universe. Violations of these rules are not merely impossible, they are forbidden by the geometry of reality itself. The behavior of the universe is not random, it follows the dictates of symmetry. Every mathematical symmetry is a rule of existence, and every particle obeys these rules. This perspective forces us to rethink the meaning of physical laws. They are not commands imposed upon reality, but constraints born naturally from the self-consistency of abstract structures. It is not that matter is told to follow certain rules, but rather that only those patterns of matter that obey the underlying symmetries can emerge in the first place. Therefore, symmetry does not just describe reality, it is the selection mechanism for existence itself. Infinite universes may be mathematically possible, but only those permitted by symmetry are stable, structured, and habitable. Our universe belongs to this class not because it was chosen, but because its symmetries allowed it to exist. However, within this sacred order, mysteries remain. Why these specific symmetries and not others? Why so, 3, instead of a larger group? Why do subtle violations like CP violation exist, introducing asymmetry into an almost balanced world? These are the frontier questions of modern physics. Theorists are searching for a grander, unified symmetry from which all others emerge. Some imagine a symmetry beyond the standard model waiting to be discovered, like hidden roots nourishing all visible branches. Others turn to string theory, where symmetry vibrates in hidden dimensions, determining not only the particles but the very nature of space-time. Some dream of higher dimensional exceptional Lie groups or E8 algebras that might harmonize gravity with the quantum realm. In every exploration, symmetry is the compass, the voice whispering from the void that says, follow invariance, and the truth will be revealed. Group theory studies change, and we want to know if it determines the very nature of particles and forces. Beneath the elegant framework of the standard model and the mysterious veil of quantum fields lies a domain more abstract than energy or matter. Here, particles are no longer entities in the traditional sense but pure mathematical expressions. In the crystalline view of group theory, the hidden structure of reality is not composed of atoms or strings, but of symmetries and transformations. Everything is encoded in the silent logic of algebra. Group theory, the mathematics of symmetry, has become the master key to unlocking the identity of particles and the orchestration of their interactions. The core concept is simple: a group is a set of operations that can be performed and undone within a framework of rules. But when this concept is extended to continuous transformations, rotations, phase shifts, and internal changes, it blossoms into the architecture of everything. Lie groups, named after the mathematician Sophus Lie, capture these continuous symmetries in smooth, infinitely small transformations, defining the laws of motion and the seamless interaction of fields. These groups do not describe particles the way a chemist describes an atom, they determine what a particle is, reducing identity to a position within an abstract algebraic space. Mass, charge, spin, and interaction strength are not intrinsic properties like color or shape, but are the results of how a particle transforms under specific symmetry group operations. Particles are shadows cast by deeper symmetries in a mathematical void. To understand this is to confront one of the most radical propositions in science, that the complexity of matter arises entirely from patterns of transformation. The standard model itself is a cathedral built from three symmetry groups, SU, 3, SU, 2, and U, 1. Each represents an internal symmetry, a way to transform a field while keeping the physical essence unchanged. This invariance paradoxically generates observable phenomena. U, 1. Symmetry supports electromagnetism, governing photons and charges. SU, 2, governs the weak interaction, responsible for radioactive decay and the sun's energy. SU, 3, commands the strong force, binding quarks into protons and neutrons via gluons. These are not philosophical concepts but mathematical structures with concrete rules. Every known particle fits perfectly into these groups like a note in a musical scale. For instance, a quark is defined by how it transforms under SU, 3. They have three colors not because of visual hue, but because SU, 3, provides three fundamental transformation labels. The gluon is essentially a generator of the SU, 3, group, a mathematical operator that maintains the group symmetry. Similarly, leptons like electrons and neutrinos belong to the representations of SU, 2, and U, 1. Their interactions are dictated by how these groups combine. There are no hidden layers, the behavior of particles flows directly from the algebraic properties of the groups they inhabit. Even the quantum numbers we use to describe particles, such as hypercharge or isospin, are not arbitrary but arise naturally from the group structure. The reason an electron has a precise charge, YW, and Z bosons have mass while the photon does not, and the very existence of the Higgs boson, can all be traced back to how these groups are broken or kept intact. In this algebraic landscape, symmetry breaking is the starting point of differentiation. Before symmetry breaks, particles are indistinguishable. When it breaks, mass is born. The Higgs field is the heart of this process. As a scalar field, its vacuum expectation value breaks the SU, 2, and U, 1, symmetry, giving mass to bosons while preserving the massless nature of the photon. This is a precise operation encoded in group theory. The vacuum itself is a decision point in an infinite symmetry space. Furthermore, group theory explains why certain interactions are permitted and others forbidden. Conservation laws, such as the conservation of charge, are the natural results of the invariance of the Lagrangian, the mathematical object describing a system's dynamics under group transformations. The universe is a constrained structure where every process follows algebraic laws. Particle decays and reaction probabilities are pre-written in the language of group representations. Even when particles change identity, they follow paths permitted by symmetry. In this sense, the universe is like a massive multidimensional Rubik's cube, where every rotation is governed by group theory. Higher symmetry groups predict new particles and relationships that, if discovered, would prove the universe is even more unified than we imagine. In string theory, particles are vibrating strings whose patterns correspond to representations of massive symmetry groups like E8. Here, geometry and algebra merge, suggesting that space-time itself is an emergent property of group dynamics. The universe is a result of symmetry folding and twisting in mathematical space. Matter is the endpoint of mathematical necessity. Reality is not composed of things, but of relationships, how fields twist and turn without violating the hidden constraints of group theory. Understanding the universe is not about knowing what it is made of, but how it transforms and maintains balance. Every particle's dance is choreographed by an algebraic symmetry written on the fabric of existence. The universe is not a machine, it is a proof, an unfolding argument from premise to conclusion, defined not by shapes but by the symmetries that define what is possible. The quantum world is expressed through operators and wave functions, and we must ask if these are the totality of that world. The quantum realm is strange and counterintuitive, yet remarkably precise. Here, objects do not have definite positions until measured. Particles exist in multiple states simultaneously, and causality seems to hang on a thread of probability. But within this apparent chaos, quantum mechanics operates with eerie precision because it is the language of reality in its purest mathematical form. At its foundation is the concept of Hilbert space, an infinite-dimensional vector space that holds the wave functions of particles. Every quantum state is a vector in this mathematical universe, determined by probability amplitudes rather than coordinates. These amplitudes are complex numbers with magnitude and phase, allowing them to interfere and weave the rich tapestry of quantum phenomena. The square of the amplitude gives the probability of an observation, but the true mystery lies in their ability to interfere constructively or destructively. This allows a particle to explore all possible paths simultaneously, only settling into a determined result upon observation. In the geometry of Hilbert space, this behavior is entirely natural. Operators are the mechanisms of change and observation. While classical systems evolve according to differential equations, quantum evolution is governed by the Schrödinger equation, where the Hamiltonian operator determines how a state evolves over time. Measurement is not a simple look inside a box, it is a projection operation where an operator collapses the state vector into one of its eigenstates. The measured value is associated with Hermitian operators, ensuring the results are real and observable. Before measurement, the system is a superposition of all possible states; after, it is a single reality. Entanglement, perhaps the most puzzling feature, arises naturally in this mathematical playground. When two systems are described by a joint wave function, they cannot be described independently. Their correlations remain consistent regardless of distance. This is not action at a distance, but a property of the joint wave function. Measuring one part instantly changes the probability of the other because the mathematical structure does not allow their states to be separate. This non-locality does not violate relativity because it acts on information, not causality. The algebraic architecture defines the rules. Quantum field theory further reinforces this, treating particles not as objects but as excitations of underlying fields. These fields are operator-valued functions defined on spacetime, and their dynamics arise from path integrals and Lagrangian densities. Every particle is a result of field quantization, and their interactions are terms in the Lagrangian that respect specific symmetries. The universe, at its most fundamental level, functions like an algorithm following rules set by operator algebra and probability flow. Quantum tunneling is a perfect example. In classical physics, a particle cannot cross an energy barrier higher than its own energy, but in quantum mechanics, the wave function has a non-zero amplitude beyond the barrier, allowing the particle to exist on the other side. This is not a physical mechanism of breaking through, but a consequence of the mathematical solution. The universe obeys this logic, suggesting that physicality is emergent rather than fundamental. Phenomena like the Casimir effect and virtual particles are explained by vacuum expectation values and algebraic renormalization. These are not tricks to describe reality, they are reality. If the quantum world consists entirely of mathematical objects, then reality itself is the instantiation of a mathematical structure. There is no deeper layer beneath the wave function. Interactions are the necessary products of internal consistency. Quantum mechanics defines what behavior means. Mathematics is not just a tool used by the universe, it is the blueprint. Once you accept superposition and unitary evolution, the rest follows with logical necessity. We are faced with a profound realization: everything energy, matter, identity is born from mathematical abstraction. We are not observers of a material machine, but participants in a vast mathematical tapestry that is being calculated, not merely built. Geometry defines space, and we wonder if geometry is the source of space-time and matter. Imagine a universe where geometry is not a byproduct of physical form but its origin. Space is not a container for matter, but matter is the expression of the shape of space. In this view, geometry is the world itself, encoded in a primal grammar. This idea evolved from the concept of a flat world to the realization that higher dimensional geometry might be fundamentally real. General relativity was the first major step in elevating geometry to a physical law, revealing that gravity is not a force but the curvature of space-time. Matter tells space how to curve, and curved space tells matter how to move. This elegant union replaced invisible forces with the weaving of a four-dimensional reality. A black hole is not an object but a geometric extreme. To study shape is to study essence. As physicists try to reconcile quantum mechanics with gravity, deeper geometric theories emerge. At the Planck scale, smooth space-time fails, leading to the idea of quantized geometry. Loop quantum gravity suggests that space is composed of discrete loops, forming a spin network. This is an abstract combinatorial geometry where area and volume are quantized. These networks evolve through time into spin foams, giving rise to the eternal fabric of space-time. Here, the universe is woven from geometric units of nodes and connecting edges, much like pixels on a digital screen, but governed by algebraic rules and topological constraints. There is no smoother space beneath this. Geometry itself is quantized into a connecting lattice ruled by mathematics. An even grander geometric vision comes from string theory, where the fundamental building blocks of the universe are not zero-dimensional particles but one-dimensional vibrating strings. Every vibration mode of a string corresponds to a different particle. Their mass, charge, and spin all originate from the geometry of these vibrations. To ensure mathematical consistency, these strings must exist in 10 or 11 dimensions. These extra dimensions are not arbitrary additions but theoretical necessities, described by complex geometric forms such as Calabi-Yau manifolds. These exquisite multidimensional shapes are not just mathematical curiosities, they determine the physical attributes of the universe. How they fold, twist, and interconnect defines the spectrum of particles, the nature of forces, and the constants of physics. The universe we see may simply be a three-dimensional shadow projected from a richer, higher-dimensional geometry at the subatomic scale. The implication is staggering: the source of everything, particles, fields, and forces, is woven from the topology of invisible dimensions. The holographic principle brings an even more radical geometric reassessment of reality. According to this principle, all information within a volume of space can be described by the information on its boundary. This concept, born from black hole thermodynamics and formalized by the duality between anti-de Sitter space and conformal field theory, suggests that our three-dimensional universe might be a projection of a more fundamental two-dimensional geometric structure. In this holographic model, volume itself becomes an emergent property originating from a perspective on the boundary. Geometry here is not just a scaffold for space but a grammar of information, a way for data to be organized and distributed across dimensions. This has sparked an exploration into the geometry of entanglement, where patterns of quantum entanglement constitute the very shape and structure of space-time. The boundaries between physics and geometry dissolve, replaced by a landscape where distance, shape, and dimension are determined by entangled information. Mathematics also explores non-Euclidean models for the structure of the cosmos, such as hyperbolic spaces and spherical manifolds. While observations suggest that space-time is largely flat, theoretical models allow for slight curvatures that determine the fate of the universe, whether it will expand forever, collapse, or remain infinite. Geometry does not just explain physical laws, it decides the destiny of the cosmos. Research into topological quantum field theory shows that the geometry of space also affects the properties of physical fields, producing exotic phenomena like topological insulators and anyons. These are stable, measurable manifestations of abstract geometry within states of matter. Geometric dualities reveal the unity behind seemingly different theories. Mirror symmetry shows that two different Calabi-Yau manifolds can produce equivalent physical theories, hinting at hidden geometric symmetries. In string theory, T-duality and S-duality suggest that large and small dimensions can be interchangeable, and that weak and strong interactions are geometrically linked. These dualities are not superficial, they suggest that the truth of reality may not lie in a single geometric description, but in the abstract equivalence between them. Geometry becomes more than reality, it is the proto-reality, the underlying substrate that transcends any single representation. Even time is being re-examined through a geometric lens. In many quantum gravity frameworks, time is no longer a fundamental parameter but a byproduct of changes in the geometric network. In causal set theory, space-time is a graph composed of discrete events ordered by causality. Geometry emerges from the structure of the network. The flow of time is not a stream but the unfolding of new connections. In twistor theory, geometry is expressed in complex space where the fundamental objects are light rays and null planes, making space-time points derivative entities. This reverses the traditional hierarchy, reinforcing the view that geometry is the origin of space, time, and matter. From the rigid abstractions of Euclidean planes to the vibrating manifolds of strings and the foamy networks of quantum geometry, the development of physics points to one revelation: geometry is not the map, it is the territory. The shape of things is not an accessory to existence, it is existence. Matter is vibrating geometry, gravity is curved geometry, and time is changing geometry. In the mathematical soul of the universe, form is function, and function is law. To unlock the secrets of existence is not to dig for particles or energy fields, but to explore the architecture from which they arise, to seek multidimensional symmetries, Calabi-Yau manifolds, entangled boundaries, and topological connections. These define not just the appearance of the universe, but what the universe is. Logic has boundaries, and we wonder if these boundaries also limit the universe. If reality is mathematical, then its architecture is not just composed of numbers or geometry, but of logical system structures of what can be known, what can be proven, and what can ultimately exist. It is in this conceptual realm that the ideas of Kurt Gödel appear like invisible cracks in a seemingly perfect mathematical landscape. Gödel's incompleteness theorems shattered the hope that mathematics could be both complete and consistent through a fixed set of axioms. His first theorem showed that in any formal system containing arithmetic, there will always be truths that cannot be proven. His second theorem went further, showing that such a system cannot even prove its own consistency. This discovery crushed the dreams of foundationalists who believed mathematics could be a self-contained, perfect cathedral of absolute truth. Gödel revealed that the mathematical universe contains hidden shadows, truths that will forever remain unprovable within the system. If the universe is governed by mathematical laws, this brings an unsettling question: does the universe itself hide truths that cannot be derived through natural logic? Are there physical phenomena that cannot be reduced to fundamental axioms? Not because they are complex, but because they are fundamentally unprovable? If we take the idea of a mathematical universe seriously, Gödel's theorem is not just an abstract curiosity, it is the boundary of existence. It implies that any ultimate theory, any grand unified equation, will inevitably leave blanks. There are corners of physical law or behavior that are destined never to be derived from foundations. Even with perfect physical laws, some of their consequences will remain unprovable within the system. This shakes the foundations of determinism. It suggests the universe may be subject to a primal architecture that cannot explain everything it grows. Like a language that can describe its grammar but cannot explain the entirety of the truth in its poetry, the mathematical universe may be filled with realities beyond logic. In this light, incompleteness is not a failure of understanding, but a structural characteristic of any formalized universe. Between what is provable and what is true, between the accessible and the real, there will always be a gap. Gödel's work is often paired with Alan Turing's halting problem. Turing proved that no universal algorithm can determine if any arbitrary program will eventually stop. This limitation is not a lack of computing power but a limit of computability itself. If the universe runs like a massive computational process, Turing's results mean some phenomena are unpredictable, not due to ignorance, but due to fundamental undecidability. The intersection of Gödel and Turing sets a fundamental limit on the dream of an omniscient equation. It paints a picture of a universe where certain aspects are inherently dark, not because of distance or energy, but because of logic itself. These theorems do not just anticipate human understanding, they draw the boundary between the knowable and unknowable reality. Gödel's influence on physics is subtle yet profound. In 1949, he used the equations of general relativity to construct a solution that allowed for closed time-like curves, suggesting the Gödel universe where time travel does not violate the equations of motion. This shows that mathematical consistency does not always align with physical intuition. Logic can permit realities that challenge our concepts of causality. The physical world may be trapped in a mathematical system where the knots born of consistency are difficult for us to explain. If logic allows for such strange realities, the boundaries of the real may not be decided by nature, but by cognition. At the heart of Gödel's thought is self-reference, a system's ability to encode statements about itself. In mathematics, this leads to paradoxes, but self-reference may have deep meaning for consciousness and cosmology. If the universe can encode knowledge of itself through observers, it is a self-referential structure. But Gödel tells us that self-reference leads to unresolvable truths. Applied to the cosmos, this may mean that as science tries to understand itself, it will encounter logical boundaries. Some questions may never be answered by empirical investigation because the system cannot contain all proofs of its own truth. Mystery is therefore not temporary, it is fundamental. This also challenges the nature of physical laws. If laws are mathematical propositions and mathematics is subject to incompleteness, then the laws themselves may not be ultimate. Nature may have constants, such as the fine structure constant or the mass of an electron, that cannot be derived from deeper axioms. They are real, yet unresolvable within the system. If so, the quest for an ultimate explanation will meet a conceptual end. The universe may function with precision, but the reason for that precision will forever transcend internal logic. The multiverse hypothesis is relevant here. Each universe might be a different axiomatic system, each with its own Gödelian blind spots. We may be unable to perceive other universes not because they are far away, but because their axioms make them logically invisible to us. Conversely, certain universal truths may only exist at the meta-level of the multiverse, much like certain mathematical truths transcend any single formal system. Gödel's theorem tells us that no universe, not even the multiverse itself, can be both self-consistent and complete. There will always be truths floating outside the formal grasp, dancing in the abstract mist. Reality, in the face of incompleteness, becomes elusive. If the universe is the output of some generative process, whether cosmic code or divine computation, there will be truths that are true but undecidable. In a simulated universe, this means some phenomena are not products of the rules, but of the meta-rules controlling the logic, which the entities within can never derive. In the rigor of mathematical logic, Gödel accepted the paradox of all knowledge systems: truth is broader than proof, and reality is greater than understanding. If the universe is mathematics, it cannot be both all explaining and all consistent. This is not darkness or ignorance, but a structural necessity of mystery. Gödel did not impose a limit on mathematics, he revealed its nature. In doing so, he may have uncovered the deepest secret of the universe, that the end of logic is not the end of the search, but the beginning. Existence and truth are connected, and we wonder if truth is the totality of existence. As we reach the end of our exploration, crossing beyond particles and fields, beyond the fluctuations of space-time geometry, beyond the hidden logic of algebraic symmetry, and beyond the abstract structures of quantum phenomena, we find a startling truth: the universe may not just follow mathematical rules, it may, in its essence, be a mathematical system. This is not a metaphor, it is an identity. The world we see, the expansion of galaxies, the rotation of the moon, the entanglement of photons, the curvature of space-time is not just mirrored by mathematical language, but born from it. Every observable fact is supported by an invisible scaffold of relations, patterns, and structures rather than matter. In this view, matter is no longer fundamental. Particles are not the smallest units of reality, but expressions of symmetry in abstract mathematical space. Forces are not entities, but the results of how these spaces curve and connect. Time is not a fundamental clock, but an emergent process in the flow of relationships. To consider a mathematical universe is to blur the line between the real and the abstract. If everything physical can be reduced to interactions, and interactions to rules, and rules to relationships, then the material world dissolves into a landscape of logical self-unfolding. In this reality, space becomes a coordinate system of meaning, where every point is defined by its relationship to all other points, like the interplay of notes in a symphony rather than stones in a desert. The void is not empty, it is a canvas of quantum fields, a presence composed of vibrating equations. Physics is elegant not because the universe happens to be understandable through math, but because it is math. Mathematics is not a tool external to nature, it is the skeleton of nature's birth. This concept challenges the ancient divide between the material and the abstract. Plato once glimpsed the realm of forms, perfect entities existing beyond space and time, while the material world was just their dim shadow. In our era, this intuition is restated in the language of theoretical physics. The laws governing black holes, cosmic inflation, and symmetry breaking are not evolving or local, they are constants that seem to be drawn from a deeper, rational realm. As our understanding deepens, these laws become less mechanical and more relational, less descriptive and more generative. An electron is not just a thing with mass and charge, it is an excitation of the lowest energy state of a quantum field, defined by mathematical rules. Its identity is contextual, like a note defined by its position in a scale. When we peel away the layers of experience, we find ourselves not in a laboratory, but in a cathedral of logic, where theorems illuminate the cosmos more deeply than light. To claim the universe is mathematical does not deny mystery or meaning, it amplifies them. If reality is rooted in math, then existence is an expression, a theorem being unraveled, an equation being solved, an infinite analysis unfolding in logical form. In such a universe, consciousness is not an anomaly but a recursive structure in the flow of information, a moment where the universe reflects on its own logic. We are mathematics thinking about itself. Perhaps the emergence of consciousness is the point where the universe achieves self-reference, incorporating the observer into its equations. This leads to the ultimate question of existence: What is the nature of mathematical creativity? Are we discovering eternal truths or inventing structures in the space of logical possibility? When we build theories of information, non-Euclidean geometry, or higher dimensional algebras, are we expanding what can be true or exploring the paths that consciousness is destined to walk? If every consistent mathematical structure has its own internal logic, then perhaps everyone derives its own reality, a parallel universe with its own laws and forms of intelligence. Our universe may be an island in the ocean of mathematical possibility, selected only because it can nurture complexity and observers. In this light, existence is not accidental but a mathematical necessity, where rules allow for richness, reality blooms. Yet one question remains: why these equations? Why the Lagrangian of the Standard Model? Why these specific constants and dimensions? Within the system, as Gödel's shadow reminds us, this cannot be answered. Perhaps it is not a question of why, but what. Even so, this realization does not diminish the profound experience of living in a rational, logically constrained universe where numbers resonate with existence. Here, beauty in an equation predicts a phenomenon in the sky, and patterns on a chalkboard become particles in an accelerator. Numbers give rise to quarks, and symmetry gives birth to gravity. This reshapes our place in the cosmos. If the universe is mathematical, we are not outside observers, we are part of the structure. Our minds are not flaws in the system, but local configurations of logic capable of reflecting the whole. We are the universe thinking about itself. Our questions and answers together constitute this endlessly unfolding equation. Ultimately, this journey through the mathematical soul of the universe does not leave us with a sense of finality, but a sense of harmony. Parts of the universe may be difficult to solve, but they are never arbitrary. It is understandable because it has structure. Its secrets are not blanks, but invitations to explore a deeper world of relationships. In this exploration, we are not spectators, we are agents of the system, part of the cosmos woven from logic and form. The universe is not a material object, it is a statement, a massive problem being solved. When we seek to understand it, we are not just solving a puzzle, we are answering the most beautiful equation of all, the one that includes ourselves. Existence may not be made of atoms or energy, but of truth. And we are the questions the universe asks itself, and the answers it forever unfolds. That is all for today's sharing. I hope you have a beautiful dream. See you next time.